Okay. So, Son, are you ready? Can I?
Yes, I'm ready. Go ahead.
Okay, welcome everyone. Today we're very happy to have some Hartnoll, who's gonna tell us about Planckian transport. So as usual, just you can ask questions. Just unmute yourselves when you want to ask a question, and that's it. So, Son, please go ahead. Thanks a lot.
Great. Yeah. So indeed, please, questions. Totally fine. Please ask questions. Good. So I will talk about Planckian transport. Let's start way back. So with simple things. So copper conducts electricity, as you know, and it has a resistance. All right. And so here's a plot of the. Let me see. Why is this not working? Let me charge my pen. So copper has here's a plot of the resistivity of gold and copper and silver against temperature, and it has this. Why is this not working? Oh, I know. Sorry, my bad. Very good. And it's roughly, so it's the resistivity against temperature, and it's roughly linear in temperature above, I don't know, 100 Kelvin, 50 Kelvin or so. Now, this T-linear resistivity has been understood for a long time. I believe it goes back to 1913. It's like pre-quantum mechanics. And it just has to do with the fact that the electrons are moving through the crystal. The atoms in the crystal are vibrating. Okay, how much are they vibrating? Well, at high temperatures, these vibrations are classical, and so they obey the equipartition theorem. Okay, so their potential energy? What's the potential energy? It's the spring constant of the atom that's vibrating times its displacement from equilibrium, and equipartition says that this is of order kBt. All right, so the kinetic energy of the atoms is of order kBt, and so that means their cross section, the size that the electron sees, right, is given by this displacement squared, right? That's the size, the sort of transverse size of the atom, and using equipartition, that's kBt over the spring constant. Okay, so again, the cross section that of an atom, of a vibrating atom that an electron sees, grows linearly with temperature, and that's essentially why this thing goes up with temperature. Okay. This was understood, no quantum mechanics here a long time ago. Okay, and so now if you want to be a bit more precise, the resistivity is determined by the Juda formula. And so the resistivity is the mass, the number of carriers, the charge of the carriers, and their lifetime. And so if you take that plot on the previous page and you put in things that you know, how many electrons there are, what their mass is, you'll find that the tau that you extract is given by this quantity, hbar over kBt, okay? Even for copper. And so so even for a very good conductor, so copper has a very long mean free path, okay? It's a good metal, that's why we make pots and pans out of copper sometimes. But this lifetime is actually very short, okay? And so let's just think about why a long mean free path can combine with a very short lifetime. Think about that. But before we do that, let me this was all understood a long time ago, as this very nice paper by Piles, you should all read it, where what he was worried about was that maybe at room temperature, the mean free path of, the lifetime of the electrons in copper might be so short that perturbation theory might not be valid. Okay, that's what he was worried about. And so he wrote down this condition for perturbation theory to be valid, which is that the lifetime in Planck units should be less than the temperature. And then he went and he looked at this ratio, right? So this is the lifetime sort of in the decay rate in units of the temperature. And for all these conventional metals, copper and so on, the ratio is basically 1. Okay, and that's the statement that for all of these materials at room temperature, the lifetime is of order hbar, kBt over hbar. Okay, that's that. These numbers 1. And then there's a footnote saying that this just follows from dimension analysis. Okay, so let's do the dimension analysis. It goes like this. And this will come back to our previous point that these are very good metals, but they still have very short lifetimes. And it goes because, so the lifetime is related to the mean free path by the velocity, obviously, right? The mean free path is the velocity times the lifetime. Okay, so let's think about these two things separately. The mean free path, what's the mean free path? Well, if we have a bunch of centers that are scattering things, and they have some separation, there's some density of these, let's call that A, some density of scatterers, let's say these are the atoms in the lattice, and each atom has a cross-section A for hitting it into, the mean free path, the inverse mean free path is given by this. And so let's check it has the right units, right? This is 1 over length, a density is 1 over length cubed in 3D, and the cross-section is length squared, right? So this makes sense. And if the cross-section gets bigger, the mean free path gets smaller. And if the density of scatterers goes up, the mean free path also gets smaller. Okay, so this is a reasonable formula. So I already gave you the formula for A. That's kBt over the spring constant. And the density of scatterers is roughly 1 per unit cell. So that's roughly 1 over A cubed. Okay, now let's do the slightly non-trivial step and say, well, where does the spring constant come from? What is actually holding the lattice together? Well, it's the electrons, right? Some could be covalently bonded or whatever, it doesn't actually matter. And so it's reasonable to estimate the binding energy, which is Ka squared, right? That's the energy, potential energy between two atoms separated by A, as some electronic energy scale T, because it's electrons that are binding the atoms together at the end of the day. Okay, so so now there's no hbar here. Okay, they're just energy scales. What's the velocity? Well, the velocity is the Fermi velocity. And if the Fermi surface is relatively large, the natural velocity is this one. For example, if you have a hopping term, if you have a Hamiltonian with like a T, C dagger I, C, I plus 1 kind of term, right? The velocity that corresponds to that is this one. Okay, assuming if you sort of filled out most of the states. Now here, there is an hbar. So you take this formula and you divide it by this one and you'll get that. Okay, plug it into here. The T's cancel, right? And there's the A's cancel, and there's an hbar left over. So roughly, the reason that the scattering rate is quite large, okay, the lifetime is short in copper, even though the mean free path is long, is because the velocity is so big. Okay, copper has, the electrons move really fast in copper. There's a 1 over hbar in the velocity, right? And that's because of Pauli exclusion. Normally at low energy, things move slowly. But in the metal, because all the excitations are at the Fermi surface, which has a momentum, they move very quickly, okay? And obviously, the quicker you move, if you have a certain number of things you're bumping into, the quicker you move, the more things you hit per unit time. And so the mean free path is short, okay? So, all right, so the scattering rate in copper is large because the velocity is big, all right? So, okay, so that's...
sorry, can I ask you something?
Please, go ahead.
Imagine that you have one of these, like, I don't know, these metamaterials that people is just like discussing right now. Just some of these lattices that you construct and you put like some classical ball that you can put in the system. I mean, just like literally a classical lattice with some balls that can jump from one vertex to another one. So are you telling me that then in that case, I cannot define something like a Fermi velocity for the system?
I didn't, let me
because
see.
I mean, to define the Fermi velocity, you are going like to the microscopic lattice system, assuming that it's quantum. But what if it's not?
Okay, so what would happen, for example, for non-degenerate electrons is that this velocity would be something like, well, there's several things could happen. But one thing that could happen is this velocity would be something like the square root of T over M, right? So because, for example, if I have just a classical ball, right, then its kinetic energy, again, by equipartition is kBt, right? And so the velocity, the thermal velocity would be kBt over the mass. So that's a typical classical velocity of a thermally excited quantum particle, and there's no hbar in it. So all the, of course, this formula. So very good. In fact, you can use this formula. That's right. So you can imagine in a semiconductor, the electrons might be non-degenerate, so that they're basically classical, okay, because the density is very low, and so you easily go above the Fermi energy, and then the electrons would be classical as well, okay, and then you would not get this hbar. I mean, this formula. So that's not, in fact, that's the point. This formula would be the same. This formula is the same, but the velocity would be slower, probably. Okay, so what's all I'm saying, the only place where quantum mechanics came in was that the well, of course, I mean, the binding is quantum mechanical and everything, but the most direct place where quantum mechanics came in is that it makes the velocity large. So if you put in another velocity, which your billiard balls would probably have another velocity, you probably would not get this Planckian rates.
Yeah, but exactly that was the origin of my question. So because then if you're assuming that temperature is large, that then it's like basically describe everything classical. Why do you?
Good. No, but okay, very good. So the nice thing about a metal, right, is that the Fermi energy is like 10,000 Kelvin, right? And so room temperature, the temperature is large, but it's small compared to, it's large by lattice scales. It's bigger than the Debye temperature, but it's much smaller than the Fermi temperature. So the electrons are still degenerate and quantum. So there is metals are quantum mechanical at room temperature.
Okay, thanks.
Very good. Any other questions? So all this was understood a long time ago, but I think it's fair to say that broadly speaking, it was not, at least not high up in people's minds for a long time. And so now let's jump a few decades forwards, and let's talk about high TC materials. So these also, you can have a resistivity that's linear in temperature. That's these plots. They're superconducting, right? So for example, here the resistivity is 0, it's superconducting, and there's some transition, and then it starts going up linearly in T, right? And if you use the Judah formula and these materials, you'll again find that the time is hbar over kBt, the characteristic lifetime underlying these materials. However, most people that would, I mean, well, remains controversial, but the general belief is that it's probably not phonons, not atomic vibrations, and there are a couple of reasons for that. One is that unlike copper, the mean free path is now very short. Okay, so the lifetime is the same, but what happens in these strongly correlated materials is that the Fermi velocities are much slower. Okay, and so they have the same, and so that's and the resistances are much bigger actually. So if you look at this axis, okay, it's probably not, I don't know if it's going to be in the same units. This may not be useful, but it turns out this axis is much, these numbers are much bigger than the ones for copper. Copper is like down here somewhere in this plot, okay? The resistivity is much bigger, and that's because the mean free path is much shorter, okay? Even though the lifetime, but perhaps surprisingly, okay, curiously, the lifetime is the same, right? So, but the Fermi velocity is much shorter, and the mean free path is much shorter, but the lifetime is the same, okay? And so the paradigm that people would more tended to have for cuprates and so on is that it has something to do, this timescale has something to do with quantum criticality. And one evidence for that is that various quantities show scaling as a function of omega over t. Okay, this is omega over t. And so maybe I won't go into this into detail, but we can look at the resistivity as a function of frequency. This is like 1 over the conductivity. So it's like the AC resistance, if you like. And you can look at the lifetime of the particles also as a function of frequency. And what this plot is trying to show is that you plot it against omega over t for different temperatures, and the curves, more or less collapse. And so the claim that this plot is trying to make. I mean, collapse is never very perfect, but the claim it's trying to make is that it's only a function of omega over t. And similarly, this is the lifetime, the frequency-dependent lifetime of the single particles that, as measured by ARPES. And again, this is omega over t. This is the imaginary part for different temperatures. And again, the claim is that it collapses onto some curve. And all I'm trying to, the point of saying this is that the t linearity here, which is out the front, seems in these cases to be tied up with some kind of scale invariance, which would not be the case in the Phonon problem. Because it looks a bit, so that I'm trying to tell you two ways in which it looks different. One is that the mean free paths are much shorter, and second is there's some evidence perhaps for some kind of something quantum critical. That said, people's attentions were drawn to this issue by this plot that made by Andy McKenzie and friends a few years ago now, where they basically just put everything I've just told you with some more materials on the same plot. So here, this axis is the Fermi velocity, and this is what I've been telling you, that it changes, right? So it's like 10 to the 6 meters per second in copper, 10 to the 5 meters per second in a cuprates, maybe, and even less in some heavy fermions. These guys are heavy fermions. Okay, so there's a big change in the Fermi velocity and in the mean free path. Okay, so these guys have a long mean free path, these ones have a short mean free path. But the lifetime, this axis is a bit counterintuitive, but what this line says is that within a factor of 5 or so, all of these materials, which have a T-linear resistivity, have this lifetime. Okay. Now, I think most people would have said that it's just a coincidence because these ones have to do with phonons and these ones something deep with quantum criticality. But nonetheless, it's somewhat striking that they all lie on the same curve, and that is a trigger for thinking maybe there is some universal principle at work in this plot. Yeah. Any questions about that? All right. So, and just to there's one more thread to weave into this story, which is the quark-gluon plasma. So around, well, actually now we're jumping back to like 2004, 2005 or so, and so the quark-gluon plasma is a deconfined state of QCD, right? And so you're at high temperatures, and the quarks and the gluons are just wandering around freely. Well, not freely, but they're not bound. And it's the measured fact is that this viscosity over entropy density turns out to be of order hbar over kb. Now let's just, I think there's a more useful way to think about this, which is in terms of a diffusivity. So what the viscosity measures is the transverse momentum diffusivity. So momentum is a conserved quantity in a plasma. So if I have some momentum, I can send it to you. And the viscosity is a measure of how easy it is to do that. It's like a conductivity. So viscosity is to momentum what conductivity is to charge. Okay, so and let's think about honey, right? You have two plates. In honey, you move one of the plates. So I'm injecting some momentum into the system, and then the other plate will start to move, right? Because the momentum got transported from this plate to this plate transversely, right? The momentum is going this way and it's dragging. And so that's intuitively why a viscosity is related to a momentum diffusivity, transverse momentum diffusivity. So in fact, in a relativistic theory, this is the formula. It's c squared and it's 8 over s. And so 8 over s being h bar over kbt is the same as the diffusivity being c squared times this Planckian time. And of course, c is the characteristic velocity for a relativistic system. And so we think of the diffusivity as a velocity squared times a time. There's again, this is equivalent to saying there's a Planckian time in the quark-gluon plasma. So, so the word Planckian was coined by Jan Zahn in 2004, and he doesn't explicitly mention the quark-gluon plasma in this, but I think there's definitely an implicit analogy. In fact, this is the same year as the KSS paper. Okay, so you know, the causality is not totally clear, but he mentions, like, he uses the word viscosity, which is not a common word to use in the context of metals. And so I think it's fair to say there's an implicit analogy made. between this quark-gluon plasma and the cuprates. And so he used the word Planckian to refer to this timescale. Tau is hbar over kBt equals tau Planck is equal to that. And the word has two meanings, I think about it. So it's Planckian because there's an hbar, Planck's constant appears, but also it has this connotation of the Planck time in quantum gravity, which is like the shortest time, right? And so the idea is that this Planckian time, all sort of physical timescales in a many-body system might be bounded above, right, by this timescale. So it's like the Planck time, but for many-body thermal systems. Okay, and so I guess the sort of implicit conjecture made here is that QCD and the cuprates share this fact that they're kind of maximally dissipative in some sense. And actually, this formula had previously appeared in Subir's book. And so, in particular, if such a bound exists, it would imply the KSS bound. And I'm not talking about prefactors. I'm just talking about squiggles at the level of squiggles. It would imply the KSS bound. Okay, but this would also have consequences in condensed matter, right? So the idea, the statement here is not that 8 over S is important necessarily. The statement is not necessarily that 8 over S is important in condensed matter. Right? Probably it's not, because probably translations are strongly broken by the lattice. Okay, the statement is that there's a meta principle, which is this Planckian principle, which applies both to relativistic plasmas and to strongly correlated metals. Okay. All right. So then actually this paper was the motivation for making this plot. Okay. And it was kind of as an afterthought, I think, that they decided to add some conventional metals. And I think they were a bit surprised that the conventional metals ended up on the same plot, although it shouldn't have been a surprise because it had been known before. Very good. Okay, so this is 2004. You know, this other paper was 2013, and then slowly things took off. And in 2018, Plankian started appearing in the titles of papers. The point of this slide is that if you wanted to have an editor's suggestion in PRL in 2019, it'd be a good idea to put the word Plankian in the title. Okay. All right. So here, this is an experimental paper on cuprates, experimental paper on magic angle graphene. These are theoretical papers, but this idea of this Planckian timescale, that it might be something that has a life of its own, has just started to take off in the last few years. Although, as I tried to tell you, it's an idea with deep roots. And I think this whole program definitely got a indirect boost from the chaos bound, which is a Planckian bound, right? So the chaos bound of Madasina, Schenker, and Stanford says that there is a time scale that's bounded by this Planckian time, and it's this Lyapunov exponent. Okay, and this inspired some thoughts that there might be connections between many-body quantum chaos and transport. But I think it's definitely still an open question if there's any connection between this Planckian bound and the kind of Planckian bound you'd need to bound the viscosity, for example. But it definitely, involves similar concepts. All right. So this is not the direction we're going to go in today, though. But that's an interesting direction. Okay. So that's sort of like let's see how am I doing for time. Perfect. That was kind of the background, and now I want to kind of pull these threads together in a way. So if there are any questions, now would be a good time.
Hi, can I ask a question? I mean,
Yes, please.
A little bit, it looks like real dimensional analysis. You have, H bar and K and T, and you want to write down something with dimension of time or 1 over time, and that's one thing you can write down. But I guess the point is that this prefactor should be a number of order 1 or some, in some. Can this be more precise? Because you could multiply it by 100 or divide by 1,000 or something.
Okay, so let me just say two. I agree with what you just said. So, but let me make two. I think there are two separate points there. So one is that in metals, there definitely are other scales that are like the Fermi energy is always there, And it is not trivial that you only, in that way, I think the quark-gluon plasma is more trivial in a way, because you know, some masses are relatively small, then temperature is the dominant scale, and yeah, what else could it be? But that is not the case in a metal. And actually, in most theories of quantum criticality in metals, I mentioned quantum criticality, but actually, I'm just going to use this page because it has some blank space. It's a bit of a lie, actually. So in a bosonic system, it's true that quantum criticality is equivalent to I'll come to the prefactor in a second, is equivalent to this scale. But actually, in a metal, you have this Fermi surface, and the quantum criticality involves some kind of scaling towards the Fermi surface, and the KF does not drop out, actually. And so, for example, in these so-called Hertz-Millis theories, in like these which are completely quantum critical and scale invariant and everything, the lifetimes typically go like temperature to some non-trivial power, inverse lifetimes. Okay, and so it is by no means automatic that even with scale invariance that you get this in a metal. Okay, that's so this is in a CFT, this is trivial, but in a more general sense of a more general scale invariant theories is not trivial, and actually it doesn't happen often. Secondly, indeed, the prefactor, right? So I'm being very agnostic about prefactors, but of course, if one wants something with content, like with real content, at some point, someone had better prove something with a prefactor. In practice, I can say that in the condensed matter systems, I don't think I'm aware of anything where this number is bigger than, let's say, 3, maybe. Okay, and definitely nothing where it's 100. So, I mean, I think if there is a clean, so while a bound without a prefactor is formally not falsifiable, right? Because the prefactor could be 1,000. I think the way most people would think about it is that, I mean, if there were a whole bunch of materials where you start finding a factor of 100, I would start to doubt how useful the concept is. So there is definitely an open question about the prefactor, definitely. And well, there are no theorems, right, apart from the chaos bound. But I do hope that there would be a prefactor, but I don't think it's the most pressing thing from a sort of experimental point of view, in the sense that I'm not aware of any parametrically large violations. Now,
thank you. Thanks. Thank you.
Yeah. But I agree with the questions. Like, what could be in between? Like, suppose there are a whole bunch of examples where there's a factor of 10. Now that would get a little bit. Even that's not the case at the moment. Okay, very good. Okay, so now I want to tie some of these threads back together, and I want to go back and revisit the role of phonons in the cuprates. Okay, so I set up these sort of these two classes, the conventional materials, which are Planckian because of phonons, and cuprates and friends, which are believed to be Planckian, well, which are Planckian, but not because of phonons, perhaps. But let's have a look. I want to re-examine that question. It's a bit taboo in certain circles. Okay, so I want to talk a bit about electron phonon scattering in cuprates. So let's start with an obvious fact. You know, cuprates have a lattice. The atoms of the lattice vibrate. Okay, that definitely happens, and these vibrations have every right to scatter the electrons that are moving through the metal. So phonons have every right in cuprates to produce Planckian scattering, just as they do in conventional metals, right? And so the question is why, well, if that's happening, surely we should be able to see that. And it's a bit confusing because in like copper or something, this T linear will go down. Oh, sorry, resistivity. T linear goes down, but at like some sort of the Debye scale over 3, it starts becoming much smaller. But in cuprates, if you suppress superconductivity, the T linear scattering goes down well below the Debye scale. And so down here, it's really hard to see how it can be phonons. So even though up here it has every right to be phonons, down here it doesn't have a right to be phonons, because below the debye scale, there are like very few phonons to scatter off. But there's no kink or anything here. The resistivity just goes straight, okay? And so there's actually a bit of a paradox in the cuprates that even if you believe that there's quantum criticality that's causing the scattering, the phonons should also be scattering. And this scattering of phonons should appear at about this scale, and it just additively, right? Because I've got a particle that can bump into different things, and the scatterings add, and that is just not seen, okay? And that's a really quite a confusing thing. Okay, so we're going to think a bit about this. So why don't we see it? I'm going to talk about this paper that I posted with Connie Mosatov a few months ago, and let's see what happens. Okay, so to take a few steps back first, the story begins a few years ago, where after all these Planckian bounds, at the time I wasn't very happy about bounding a lifetime or an inverse lifetime, because, well, the lifetime of what? I mean, there might not be any well-defined particles in these systems. So what lifetime are we actually talking about? And in the context of transport, I mean, there are natural lifetimes. There's the equilibration time, there's the Lyapunov time, but somehow in transport, people wanted to think about a single particle lifetime, and that's not such a nice quantity. All right, so I thought, well, what's something that's always well-defined? Something that's always well-defined is the diffusivity. Whether you have well-defined quasi-particles or not, conserved quantities diffuse unless they have sound waves and stuff. So diffusion seemed like a very robust phenomenon. And also, so in the language of diffusion, the analogy between the quark-gluon plasma and the metals looks like this. So in metals, you have a charge diffusivity, the inverse, remember diffusivity. So the diffusivity is like the conductivity, the inverse diffusivity is like the resistivity. Right? So, okay. The charge diffusivity is the fact that it's Planckian, means it has this time scale and a Fermi velocity, whilst for momentum diffusivity, in the quark-gluon plasma, you again have this inverse time scale, but then a different speed. Okay. But of course, the mother of all diffusions, the diffusion was invented to describe the motion of heat, okay, which is diffusion of energy. And in fact, that's the one that's the easiest to measure. Charge diffusion is not something very easy to measure in a metal, because if I put a lump of charge in a conductor, it just exponentially quickly goes away because of screening, okay, because of electromagnetic screening. You won't actually see charge diffusing in a metal, but heat does diffuse. And so my colleague Aaron Kapeltunik was inspired by this to go and just measure the diffusivity. And so how do you do it? You take your sample, you shine a laser with a certain frequency, okay, it's modulated with some frequency. You shine another laser a little bit far away, and you measure how much this reflects. You measure the reflectivity here. And it turns out that, so it's oscillating with some frequency. And if here, there's a phase shift in the oscillations compared to the source, and it turns out that this phase shift depends on the diffusivity. It's some simple geometrical thing. You write down the diffusion equation, you Fourier transform it, and you see that if you have two sources, there's a phase shift between them, and that phase shift is related to the diffusivity. So it's a way of measuring the diffusivity, and it's quite accurate because it's sort of, you pick out a frequency. Okay, so they did this, and it came out kind of interesting. So this is the inverse diffusivity again. So it's like the resistivity, but for heat, right? It's like the thermal resistivity, if you like, roughly. And it turns out this is temperature. These are several cuprates. Doesn't matter too much for right now. And it has this, at high temperature, has this nice linear regime again. So this is completely analogous to the linear resistivity, right? But now it's for heat. However, something kind of funny happened. So let me go back for a minute. Look here, remember I put in this sort of Planckian rate, but the velocity, there's also some information on what the velocity is. And it turned out that these things are Planckian, but the velocity that you have to put in is the sound speed. And so this slope here is Planckian, it's set by this time scale, but the velocity is turned out to be the sound speed. So that's kind of interesting because that's not the speed that electrons move at, but that is the speed that phonons move at, right? Because the sound, but the lattice vibrations. And so it suggested that this heat is not being carried by the electrons, but by the phonons. Let me come back, which is not what happens in copper, right? So in a normal metal, the reason we cook, you could cook with a copper pot, is because copper conducts heat really well. Why does it conduct heat really well? Because the heat is carried by the electrons, and the electrons are very fast. They have the Fermi velocity, right? So this fact of heat going like a sound, like set by the sound speed, is more like an insulator than a metal, okay? And in fact, this kind of behavior is actually well known in insulators. Okay, so the thermal diffusivity. Shall I question? Yeah, go.
Can I ask a question on the previous slide? So here you say that this Vs squared suggests phonons, but here what requires Vs to appear there rather than some other velocity? Some of the other velocity.
That's very good. What can I say? Yes, no, that's correct. So this, nothing requires it, and so it doesn't prove. I'm going to give you in a minute a second argument that it's phonons, but that's correct. This is just the This is the statement, and I'm saying it suggests phonons, but it doesn't. It definitely doesn't imply that phonons.
But I imagine that there's an order of magnitude difference between that sound speed and the Fermi velocity.
At least, and it's squared, right? So yeah, definitely. So right. So it's. Hang on, let me get this right. So let me get this the right way around. So if you put a much bigger velocity here, then you get a very small number there, right? So it would be very sub-Planckian. That's right. If you put a bigger velocity in, I hope I got that the right way around. Sub-Planckian meaning.
Yeah, you need a huge prefactor in order to make up the numbers.
Wait, hang on, let me get this. Did I get it the wrong way around? Right. So okay. So
to get V-1 to be of the right.
Yeah. So that
value with VF, then you need a huge prefactor in front of that after that squiggle.
Yes, that's right.
Which would undermine the logic of putting VF there.
Correct. So I'm about to give you a second argument for why it should be VS, but it's correct that this is okay. The statement is you get this. Okay, but let me tell you something. Let me go to the next slide because this is directly related. This behavior is also what you get in an insulator. And insulators have no electrons. They're only phonons. So maybe that's so what you could have been worried about is how did the phonons become Planckian, right? But let me. Okay, sorry. Step back. Wait. Let me say. So there are going to be two statements. One I'm going to make in a minute. I haven't made yet. The first one. So three statements. The first one is this is just a fact. Okay, you can write it like this. All right. Secondly, the second statement is that this is exactly how the thermal diffusivity behaves in an insulator. Okay, and in a trivial insulator like salt. Okay, or, something no spins on it, something where the only thing that could possibly be carrying heat is phonons. Okay, similar magnitude actually. So that's the second argument that you should think of it as phonons. And the third one I'm about to give you in 2 slides.
Is there any other parameter than temperature that you could vary that would help you justify why Vs is the right quantity because it varies in the right way, rather than some other velocity that wouldn't vary in the right way?
But should we take the insulator? Okay. So in an insulator, would you be happy with the phonons carrying heat? Oh, so let me see. Well, this is, I think, let's see. Yeah, you can vary. Well, things vary by factors of 2, though. So, I mean, honestly, at the level of precision that anything's being done, I don't think it's very easy. But I will. Let me try to convince you that it's phonons. Okay, because that's important for what I'm about to do. All right. So the point is completely right. I'm agreeing with your point. But let me just say it again. So this linear behavior, this high temperature behavior like this, with in fact this order 1 number here, is very well known, and it happens in a lot of insulators, and it's just due to phonon anharmonicity, right? So phonons can also scatter off each other, and this T-linear thermal resistivity is basically the same as the T-linear electrical resistivity of copper. So there it was electrons moving and colliding with vibrating phonons, but when phonons move, they also collide with vibrating phonons, and you get that this equipartition argument goes the same way. So this term looked a lot like an insulator. However, there's a difference, and so that's what this plot is. So let me explain this plot to you. These lines are the cuprates, okay? So with this linear region extrapolated to here, and these are certain complex insulators that they decided to compare to, which also have this T-linear regime, but they extrapolate to 0. Okay, the high T regime. And so this linear regime has an offset. So it's a slope plus a constant for the high temperature regime. And this constant, it turns out, is of order m star, the electronic mass. So this now looks a bit electronic. Okay, and the kind of words in this paper are there's some electron phonon soup, and you shouldn't talk about it as either electrons or phonons, but some complicated thing. So in the remainder, I want to give a sort of simple explanation for the sum of these two terms in terms of phonons. Okay, and so
ask you
yeah.
quickly, what exactly do we call m star here?
This is the renormalized mass of the electrons. So you could measure it, well, there are lots of ways. The specific heat, maybe, for example. So for example, the specific heat over temperature goes like, I think it's Kp squared m star at low T. Or you could measure it from quantum oscillations, or you could measure it, I mean,
This way we kind of assume that there are quasi-particles around.
Yeah, this is all going to be with some quasi-particles, yeah. But this is some scale that's, it's normally 3 or 4 times the bare mass, sometimes a bit bigger.
Okay. Yeah.
Can I maybe also ask you a question, Sean?
Yes.
So the lanthanum aluminate in this graph, it starts to deviate from this high temperature extrapolation around 300 Kelvin, right? And you see the same effect happening in the cuprates. Is there an explanation for this?
Yeah,
why?
actually, well, let's see. Yes, okay, which I have thought about recently. In fact, it's basically just that the ones who are below the Debye scale, that there are fewer phonons to scatter off. Yeah.
Okay, that's what I thought. Thanks.
So let me make now the third point related to what Blaise was saying about why it's phonons. Another evidence that so what the point I'm trying to sell at the moment, okay, is that heat at high temperatures in cuprates is carried by phonons, right? That's the main point. And so the third piece of evidence for this is that so in a conventional metal, heat is carried by electrons, right? And once again, that's why we cook with metals, right? Because they transport heat well. And one manifestation of this is the Wiedemann-Franz law, which is the ratio of the thermal and the electrical conductivity. And because they're both carried by the same thing, the electrons carry both the heat and the charge, they're related in a sort of universal way. That's called L0, that's the Sommerfeld number. In cuprates, however, at room temperatures, you find that this L, so this is true, so in copper, this holds at room temperature, more or less. But in cuprates, you actually find that this L, the thermal conductivity, is much bigger than it should be, at least by a factor of 3 and often by a factor of 5 or 6. And so what that means in the naivest interpretation, so you think of the thermal conductivity heat can be carried by electrons or it can be carried by phonons. If you expect that the electronic contribution obeys something like this Wiedemann-Franz law, then any surplus heat current that you see, the simplest interpretation is it is carried by phonons. Okay, so that's also consistent, right? So for me, the picture is there's thermal conductivity is relative to the electric conductivity, and this is possible because the electric conductivity is small. These are not good metals. You do not want to cook with a cuprate, okay, because the electrons are not moving around fast enough, okay, and they don't conduct heat. So there's too much heat being carried, and it's leading all the behavior at high temperature looks very much like an insulator, which means it looks like it's carried by phonons. Okay, so
Can I interrupt you 1 second?
Yes, go.
Yes. Am I wrong, or you need quasi-particles to derive the Wiedemann-Franz law?
Oh, for sure. Yeah. Well, so there are two. I think there are two. Obviously, so this pi squared over 3. This comes with some integral of the Fermi-Dirac distribution, which definitely needs quasi-particles. The idea that if electrons are carrying both heat and charge, then this ratio should be some all-in-one number is, probably more robust than that. But yeah, this is what I'm showing you some consequences of some very low-tech, simple-minded thinking about these problems.
Yes, because here there is like the subtlety that if you are trying to describe a system that you're assuming is not having quasi-particles, then expecting to have like to satisfy the Wiedemann-Franz law.
So firstly, I'm just to be, I'm not assuming that there are no quasi-particles. In fact, if anything, I'm assuming that there are in my mind, it's good to have the two hats, okay? And there's some days where it's good to think that there are no quasi-particles at all, and other days I'm going to assume there are quasi-particles because we don't know at the moment, right? And so
okay.
The story today's story is that there are quasi-particles, and we're trying to see how far we can go, or at least something that's close enough to a quasi-particle that these simple-minded things should work. Just by the way, experimentally. So if you really want to talk about quasi-particles in Wiedemann-Franz law, the cleanest thing is at 0 temperature, okay? Because there are no phonons at all. You just go to electrons. The cuprates at the critical doping, where the resistivity is T linear all the way down to 0 temperature, it obeys Wiedemann-Franz law with the pi squared over 3. All right. So that's an experimental fact actually. So just T equals 0, P equals P star. Okay, the critical doping, the resistivity is some constant plus temperature, goes like temperature. This constant term in the resistivity obeys Wiedemann-Franz at the critical doping at 0 temperature in, I think it's NdLSCO. Okay. So I do not know. I mean, that certainly smells very quasi-particle-like, but what do I know? Okay. So, but it's more. I think it is a bit more robust. It's more the level of an estimate, right? Here, I don't want to make a strong assumption. I don't care about this prefactor. I'm just saying there is more heat, quite a lot, like 4 times more heat is being transported than you would have naively guessed. Okay, that's all. That combined with the fact that the sound speed, that the order of magnitude of the thermal diffusivity looks like that of an insulator, suggests that it's phonons. Okay, but let's say we believe all this. Okay, that would explain this term. But now I want to tell you about this term, this offset. Okay, and so in a metal, this offset was there for metals, but not there for insulators. Now, a metal has electrons, and so the phonons are carrying the heat. They can scatter off the electrons. Okay, so right back at the beginning, I was talking in copper. I was talking about the electrons scattering off the phonons, but of course, phonons could also scatter off electrons. And in a normal metal, we normally don't think about this very much because the heat is transported by electrons, not phonons, and so we don't have to worry about the phonon lifetime. And in an insulator, there are no electrons, so we also don't worry about this process. But nonetheless, this process is there, right? So So we have the thermal diffusivity. We assume it's being carried by phonons. So it depends on the phonon lifetime and the phonon's speed. But the phonon decay rate has two contributions. It can scatter off other phonons, or it can scatter off electrons. Of course, there's also disorder and other stuff. This guy can easily be calculated with a sort of Fermi golden rule, simple-minded second order perturbation theory calculation. And the picture goes like this. Here's your Fermi surface, okay? And the phonons have a wave vector, okay? Which is many of the phonons is order the lattice spacing. If you can put the phonon wave vector such that it connects 2 points on the Fermi surface, then that phonon can just decay into an electron hole pair, right? You can create an electron here and a hole here, right? And that conserves charge, right? Because they're plus and minus, and it conserves momentum because you put them on 2 points on the Fermi surface. So there's some very simple calculation where you count the number of ways you can do that, and you find that the phonon electron, so this is phonons scattering off electrons now, right? Goes like it's this times some dimensionless constant. Let me come back to the constant. If this constant was order 1, okay, which we'll come back to in a minute. If that constant is order 1, if I put this in here, the VS's cancel, and it will give me exactly the offset that these guys observed. Okay, this M star offset. Okay. Okay, so what is this constant, and why might it be order 1? Right. Of course, it depends on things like the electron-phonon coupling and how strong they couple and things like that. So this is the fun. So now we're going to apply. Actually, I forget. Is it Newton's first law? No, the action-reaction. Right. So if electrons can scatter phonons and phonons can scatter electrons, it's the same coupling that's doing those two things. Right. And so there's a relationship between the forces that they can exert on each other. So suppose that you believe this calculation, and by the way, we didn't. I mean, this is from like the 50s. Okay, this result's been known for a long time. Then the experiment says that this constant is order 1. Okay, that's the experimental result. Now let's take that and let's see what that applies for the opposite process, for electrons being scattered by phonons. Okay. So here's this calculation. So this is the one I just told you. Phonons can be scattered by electrons, but electrons can also be scattered by phonons. And as you know, at these high temperatures, that's going to be given by T. And there's also a constant here. It turns out, if you do this calculation, that these two constants are the same order of magnitude. I'm not talking about factors of 2 and stuff, which hopefully is plausible, because the electron it's the same electron phonon couple. If an electron scatters a phonon or a phonon scatters an electron, it's the same interaction. I mean, it's different diagrams, and stuff. Like one diagram is the electron sort of emits a phonon, or the phonon decays into an electron hole pair. Okay, those are like the two processes. But this coupling constant is the same, right? And so if this constant is order 1, which is what was observed, this constant is also order 1, which means the electron phonon scattering is Planckian, which is what it should be. That's what happens in copper. So let me just draw this circle closed again. Way back at the beginning of the talk, I tried to tell you that the electron lifetime in copper was Planckian by dimensional analysis of scattering off phonons. Okay, so we should expect the same in the cuprates. And suppose you tell me, well, I just don't believe. Maybe phonons don't scatter in the cuprates for some reason. Okay, well, I said, okay, I cannot tell you what the electrons are scattering off, but let's look at what the phonons are doing. And I'm claiming that this thermal diffusivity sees the phonons scattering off the electrons. And it tells you how strong that is. We take that result, and by consistency, you recover the Planckian scattering of electrons by phonons. Okay, so it really is there. That's what I'm trying to say. I mean, there's nothing radical about this conclusion. Okay, right at the beginning, from almost 100 years ago, it's known that phonons scatter electrons with a Planckian lifetime. Okay, but this is not seen in the cuprates. So maybe you think for some reason the phonons are like turned off in the cuprates. Okay, But I'm telling you, it is not the case, because you can see the phonons and you can see that they scatter off the electrons. Okay, that's that. Okay, I'm almost done. Let's see. Yeah, perfect. Maybe 5 more minutes. So yeah.
At this point, so you were not discussing the offset, the Sam star or something in counterpart, but your argument doesn't touch the linear and temperature part, the phonon.
Yes, I'm sorry. Thank you. You're totally right. And the only reason is that we wrote a paper about that a year ago, and I don't have time to do everything. So indeed, you could be surprised that this term is Planckian. That it is a little bit surprising that there's not a small number here. And I refer you to our previous paper with Connie. There is a story. If I had, there is a whole other story about this term. But it's which is quite interesting. It's not what I'm talking about right now. But yeah, it's a good. Yeah, you're right. I'm not saying this term is. In fact, this term, what's a bit interesting is it's the same in insulators. So you can decouple a lot of the complicated stuff with metals and just say, I want to study heat conduction in an insulator, where it's just phonons and everything's classical. All right, so it's a little. You might be confused as an hbar. But there is. If you ask me at the very end, maybe I can say a few words about it. Okay, so let's see. Okay, so what I've been trying to tell you is that one should expect phonons to scatter electrons in a Planckian way in all metals. In cuprates, I have given you indirect evidence that they do. And there's a real paradox then, which I don't know the answer to, which is that this scattering of phonons, I'll draw again what I drew at the beginning, should only kick in above the Debye temperature. Okay, and so if we only knew about this range of cuprates, it could be, maybe it is phonons. I think, mean free paths are a bit small and stuff, but maybe it's phonons. But the problem is that it just carries on all the way down to 0 temperature without a kink. And it's very hard to see how phonons can do that, because below the Debye scale, it's much harder to populate phonons. And famous, right, the resistivity goes like T to the 5th in a conventional metal at low temperatures, right? Not like T, it's much weaker. And you should know this, right? If a boson, right, the number at high temperatures, that the number of phonons goes like T, but at low temperatures, the number of phonons goes like T cubes. And this is just like the black body radiation thing, right? It's massless bosons. And so they go like T cubed. And so there are not enough of them at low temperature. And so there's really just a contradiction here. Okay, I'm trying to tell you that phonons have to be doing something, at least here. They probably can't be doing anything here. And yet there's no feature. I mean, you just look at this thing and it's just, I mean, it's really, there's no feature. And so so we did one last thing to say about that. Okay, and so, but they've got to be somewhere. I think this is really not really an essential problem to resolve. Okay, so that's here. With most thinking optimal doping. This is the cuprate phase diagram with temperature and doping. So let's sit over here. Overdoped. Things are supposed to be more conventional there. And so let's see if there's a feature in the overdoped regime. Okay, and so this data existed. Both this is a nice paper by Ando and nice paper by Cooper. This is Hussey. And they have nice, pretty close, because I want to take a temperature derivative, right? So the data points need to be closely spaced in temperature. They did this, and actually I'm going to do an analysis that's extremely similar to what was done in this paper by Hussey et al. But it's fine. It's the same data, but I'm going to reach a slightly different conclusion. Okay, and it's so this is LSCO overdoped, way past the dome. Okay, over here. I'm over here. Okay. This is the derivative of the resistivity with respect to temperature. It's a bit noisy, obviously, right? Because it's some numerical derivative, but I think the trend is pretty clear. And so let's just focus on mine for a second. If the resistivity is a constant plus T squared, then the derivative is B plus CT. Okay. So here at low temperatures, the fact that it's linear with intercept pretty close to 0 is telling you that this at low temperature, this thing is 0, and this thing is not. So the resistivity is going like t squared with no t linear component, right? And this is t squared is what you might expect for some strongly correlated Fermi liquid, all right? However, at this scale, there's a kink. And if you extrapolate it down, there is an intercept. And this intercept is a B, which means a T-linear scattering is turning on at this temperature. Okay, suppose this is exactly what should happen with phonons. And this is actually exactly the right scale. So in this Bloch-Gruneisen formula for phonons, it becomes T-linear at about T⁵/3. I mean, just you look at the formula, that's roughly when it looks straight, okay? This thing times 3 is a very reasonable scale for phonons in cuprate, about 450, 500 Kelvin. That, in fact, in ARPES and so on, that's where they see roughly where people see phonons coupling strongly to the electrons. And so I'm going to claim that in the overdoped regime, this is exactly what it should look like for phonons. Now, what this is not, okay, is the quantum critical regime. So, which is more what this paper was about. So if you look at the phase diagram, resistivity, temperature, there's some critical fan here, okay? And the ideological claim that may or may not be true is that it's exactly T-linear in here. There's no T squared. At this doping, this temperature is super high. It's like a few hundred Kelvin, way above this temperature. So I'm down here, okay? I'm not in the quantum critical fan at all, okay? That's a much higher temperature, all right? And there's still, and we see there's still a T squared here, okay? So you go up, and here there's a kink in the resistance, which is exactly what it should. So I think this should not be controversial. You've got a Fermi liquid, and phonons start scattering stuff too at the temperature where they should start scattering stuff. Okay, so and now you can extract this T-linear term. You can look at its magnitude, and the time comes out pretty close to the Planckian time. Right. Now the fun happens when now you start moving towards optimal doping, and a very strange thing happens, which I do not understand. You know, has been well documented. But not quite from this angle, is that a T-linear term starts turning on at low temperatures. So in LSCO, for example, it's well known that in addition to this critical fan, there's also a little dome here where there's a T-linear, where it's T plus T squared. And so a T-linear term starts turning on at low temperatures. That's this line. This is already in this paper. This starts turning on. And so what happens is this line starts going up like that, right? Because this kink actually remains, but it starts getting smaller because a T-linear term starts turning on at low temperature. Remember, the intercept is the T-linear term, it's the derivative. And by the time, just before you get to optimal doping, the lines match. Okay, which is just a bit crazy, really. When I mean, it's if it's true, which, you know, I think, I don't know, maybe I'm 90% convinced. I'm not sure, but I think there's a good case for saying that this is phonons, and this thing happening down here, probably not presumably not phonons. This dome, but when you get to here, they line up perfectly, and there's no feature. Okay, and so I would say that the merging, so this Planckian phonon scattering up here merges with some kind of quantum critical scattering. I use the word loosely, and they merge at this scale. So I think this, I think this is a sort of a new perspective on this absence of a kink paradox, which is you go to overdope, the kink that you expect does appear, and then as a function of doping, it disappears again, which I think is kind of interesting. All right. So yeah, is there a question?
Sorry. Yeah, I wanted to quickly ask you something. Can you go back to the previous slide? I mean, this temperature scale that seems to follow it's your guides to the eyes that lead us to this certain scale. Let me just bear with me, because that's not the comment I wanted to make. So both in photo emission experiments, but also in optical experiments, and in my opinion, also in transport, if you look at the temperature dependence, you can analyze it in two ways. It's how you present it here as the sum of t linear and t squared components. But you can fit the same data with t to the power some exponent, as people have recently also done in photo emission experiments. This is the work from Dan Dessau's group, for example. And I think if you take t to the power alpha, with alpha between 1 and 2, the derivative, I think, gets pretty close to what you're showing here.
Okay, so let me say two statements. I definitely agree that there's, in a way, there's one way of framing it is whether can the data carry the ideology or not, right? I mean, in principle, it might not be able to, right? So I do agree that it's a human, the interpretation of the data is a human endeavor. Okay, and indeed maybe. So in fact, a few things. So Hassi examined the exact same data and reached, and indeed in his mind, he went up to higher temperatures. And so let me, where's this going to fit? Let me try to stick it here. And it's quite interesting. In his mind, what he saw in the same data was a t plus t squared, and then there was this critical region where the derivative flattened, right? So in his plots, the way he draws it, it looks like this, and then it flattens when you go into this fan. And he said, well, yeah, sometimes there's kind of some intermediate bending where you go from the t squared to no t. Like he says, there's a t squared and a no t squared, and this stuff that I'm putting this line through, in his mind, is just some, I assume, just some bending. All right, so there's an example where the same data was interpreted differently. But you know, okay, so actually in the paper, we looked at some other. I'm just showing one here because it's the furthest, the most overdoped. But some of the other ones, actually, the noise is a lot smaller in the derivative. And I think a kink is really not unreasonable. But I'm not saying, it does look pretty. I mean, kink-like. Maybe I'll try to dig it up later if you want. I've become a bit of a convert to this to taking the derivative. I think people should do it more often because it's definitely nicer than starting doing anything that involves a log, either a log derivative or a log plots or various things like that. And this is quite honest, right? I mean, you take the data, you take the difference between the points, and you just plot them, right? There's no fitting, right, in making the plots, in the plots at least. But of course, I do agree that there is some. So once again, I think the way I'd like to phrase it is that the existence of a feature at the Debye scale over 3 is something you have every right to expect, and so it's not a crazy ideology to superimpose on the data. And this data does not disprove it. There is a feature around that scale, and that feature disappears as you go to optimal doping. That's all. Yeah.
Okay.
Good.
Thanks.
Okay. Actually, it goes up. Yeah. I'll dig up. We'll dig up the other plots in a minute.
But so, Sean.
Yes.
So still, if you keep the higher temperature data, then you see that the derivative flattens. So that defines another intercept. So then what's the interpretation?
So, so that was Hassi's, that was, let's say, the ideology that was put onto this data in this paper. I'll dig up later a paper so actually Takagi has a paper from decades ago, which went to very high temperatures and also plotted this d rho dt. And it just does not flatten. Okay, I mean, so I am not convinced actually that this regime is really purely T in general. Certainly away from optimal doping. Maybe at optimal doping it is, but it's really not obvious. So I'll show you I'll show the plot later maybe.
What about the other overdoped cuprates like thallium-2201, etc.? There's lots of transport data as well.
So actually there's not. I mean, if you want to go to so I believe the BISCO is somewhat similar to LSCO from what I believe. I am not sure about others. Yeah, I don't know. It's not. Yeah, this. I think it should be looked at actually. Like careful data closely spaced in temperature with this derivative.
I think that there is transport data for thallium. This is one of these.
There's recent data. There's recent data from Nigel Hussey from this year on thallium-2201 and BISCO 2201.
Yeah. Okay. Yeah. So
they are plotting. They are plotting the rho dt
right.
also.
Let me. Okay. I really. Let's see how I can best. So let me spend 1 minute on the conclusions, and then people who want can go away, and I can quickly show you some plots. But I'm not. Yeah, I don't know how whether this flattening is a very robust thing or not. I'm not sure. Okay, so let me just summarize everything. So just 3 points. So I was saying that Planckian scattering, by which I mean just a time scale like that, arises in both the most conventional Phonon-like and also the least conventional, in quotes, quantum critical metals, and also elsewhere, like quark-gluon plasma and magic angle graphene and all kinds of stuff. And then what we've been talking about just now is that I'm claiming that in high TC cuprates, these two mechanisms seem to merge into each other at optimal doping, which may be consistent with the idea of some kind of fundamental bound, right? This is the idea that apologies if people have heard me say this before, but if you're on a freeway and all the cars are going at the same speed, it's not because their engines are identical, it's because there's a speed limit, right? And so a natural way for very different things to behave in the same way is if there's some kind of limit that they're saturating. Of course, for this logic to work, there has to be a reason that things want to saturate the limit, right? It's obvious why cars want to go fast. It might not be obvious why quantum systems want to saturate a bound, right? If you want to say a bound explains universality, you have to explain why things want to saturate the bound. Okay. And then finally, as a sort of encouragement, and coming back to Carl's comment earlier, this scale is really a universal scale. It doesn't depend on any details, right? It only depends on quantum mechanics and on statistical mechanics. And so if there is some kind of Planckian bound, it really should be, it should be provable, right? Because the ingredients are pretty simple. And I think, I think that would be a nice thing to do. All right, so thanks a lot, everyone.
Thanks a lot, Son. So yeah, this time for questions, and of course, time for continuing the discussion we had before. So yeah, free time.
Yeah, I would like to come back to some of the stuff that we were just talking about, but perhaps if there are any other questions,
yeah.
that would be
first. Maybe we can have some more general questions, and then we go back to this, if there's any. I mean, of course. So yes, please go ahead. Whomever wants a question. Okay.
All right. Let me dig up. It's going to take me just 1 minute, but not very long because I have them.
I mean, now, of course, we can stay as long as we want. You want.
Well, let me. Yeah, I don't have infinite time, but I do have a little bit. Yeah. So let's.
Yeah, that's the limit.
There we go. Okay. Where'd it go? All right. So I am going to unshare the screen and then share again. Okay. Because all right. Because I want to change.
Yeah. No problem.
Sharing. So stop. And now let's do something else. Oh, there's some comments in the chat. Are these questions by any chance?
No. It's just
no. Okay.
A link to your slides.
Perfect.
I would have told you.
Okay. So wait. Did that work?
Yeah.
What are you seeing? No, actually, I don't think it's. I think.
PRL.
Let me try again. I'm sorry. I think I shared the wrong one. it's a dangerous job. This. Okay, let's. That's the one that I wanted to share. Yeah. Okay, there you go. So this is a fairly old paper, but I think the data is not so different from some more recent papers, and I know. So this is early paper very early paper on LSVO up to very high temperatures, the resistance, and well they plotted d rho dt, and so okay, so look, this is kind of so in these dots here. So there is some flattening, which is quite consistent actually with what's in Hussey's data. There is some flattening at sort of quite close to optimal doping, to optimal, the critical doping. I got told off recently for, optimal doping is defined in terms of TC. What we're really talking about is the critical doping, which is something about, doesn't have to coincide with the optimal doping. Anyway, so around here, it's pretty, it does kind of flatten, all right? But it kind of then starts going up again later, and also if you're slightly overdoped, I mean, I don't think it's just not flat ever, and like these, this is consistent with what the more recent data, which is not to such high temperatures, looks like, which I can also dig up in a minute. So that's this is the one thing that I know, right? So again, flat means purely T-linear, right, with no T-squared component or anything else, right? And so it is there, right? They're there, but yeah. Let me show you another related to that. Let me show you this Andy Ando paper actually as well. Yeah. How am I going to find this? Yeah, this is almost.
Yeah, so while you're searching,
Yes,
I think this is very, very interesting. But again, I think what the data at in the overdoped regime shows, or you would argue that there is a deviation from linear behavior of the derivative here around 300 Kelvin.
Well, it's not linear anywhere, right? It's not flat anywhere.
No, exactly. But then there is no signature. That's where I was going for of this phonon energy scale, right?
Well, let's look. Good. Let me show you. Yes, I agree that here it looks more like but you have to go down to lower. Okay, let me. Yes, that I think I agree that if you looked at this data, it's not. But it's not very obvious.
But yeah. But again, maybe I'm just not expecting the right thing. Do we actually expect this to be a sharp kink, or is it more like a gradual crossover, which you would also expect naturally?
Of course, yeah, no, that's well. You can look at absolutely. That's right. So what you can start doing if to get a handle is to take something like T² plus block-Grüneisen, which would go from like T5 to T. Right? You could just take that, add them, and plot them, and of course. And actually, the T² is going to jump. So it's a bit complicated actually, because once you go through the debye scale, okay, so phonons above the debye scale, they scatter electrons, but below the debye scale, they don't scatter efficiently, but they do renormalize them because the phonons are faster than the electrons, and so below the debye, when the electron at temperatures below the debye scale, and so as the electrons move, they sort of drag some phonons around with them, and the effective mass of an electron, m star, gets renormalized by phonons below the debye scale, but not above the debye scale. This effective mass comes into the T² coefficient, and so it's reasonable that the T² coefficient also jumps as you cross the debye scale. So you could put all that together into a formula and plot it, and yeah, I mean, you can probably get varying degrees of kinkiness, smoothness or not to that crossover, so I don't. Yeah, right. So a feature has every right to be there, and at roughly the scale. Okay, let me try to find. I want to find two more papers, but your point's taken. I'm not disagreeing. So let me see, this might take 1 minute. Let's see, I think it's here. Yeah. And then it's here. And then it is it this one? Yeah, great. Okay, I'll show you two more. Okay, so now let me, how do I share this? Stop share, very good. And now let's share again. There's probably a better way to do this, but okay, anyway, share. All right, so this is this paper by Ando. And they actually were even braver and plotted the second derivative of the resistivity, okay, which well, you saw how messy the first derivative was, so I'm not entirely sure, but okay. Anyway, it's quite interesting. So this is our friend LSCO again, okay. And remember, if it's purely t-linear, if there's no t squared, then the second derivative should be 0, right? Because you're differentiating twice. If there's no t squared, the second derivative should be 0, which is this white. And what their claim here is that if you're at optimal doping, it looks white, okay, which is saying that it is purely t. But you just go a little bit overdoped, and there's some curvature in it, and that's quite consistent with at least up to this scale, and that's quite consistent with this Takagi data, and I think it's also in Hassi's data. I just do if you look at this plot, at least on the overdope side, you do not see a fan. I just do not see a quantum critical fan in this plot overdoped. Okay, and this kink I'm talking about is sort of here, right? So anyway, this is some other data that you can also look at. This line is some structural transition that doesn't do anything, but you see it in the second derivative. By the way, just while we're at it, it's a fun. I mean, the other thing is, it's too much. I mean, the underdoped is pretty interesting, of course, right? Because the convexity is the opposite. It has this, which is why it's blue up here. But okay, let's leave that. And so last one, I'll show you one more, and then I'll be done. Let me just. Let me just show some of the other plots from our paper to see, so you can see what they look like. Okay, and now how do I do that? Now I go to Zoom, share. All right. Good. And so this was the plot that I had showed you before. This one is the most overdoped one. And actually here, so these are the same, these are slightly less overdoped. I mean, so, I mean, that's not the worst straight line that anyone ever saw. Here. Yeah, you know what? Sorry, I think I have this will take 1 second. Right. So okay, I don't know. Yeah, and so what happens? This. I mean, I don't know. Yeah, I mean, it seems okay. That's what it is, and if you go to so this is, again, this looks like a pretty. I mean, I've seen worse straight lines than this one. And then this is the flattening. This is now getting close to the optimal doping. This is the flattening that Hassi talked about that we also saw in the Takagi data. But by the time you get, this is literally optimally doped, or 19, I think, and there's just no feature. So there is something that goes away. I think I mean, it's definitely just true that there's like a clear feature here. and it's definitely not there once you get to optimal doping. This is the close to this is 0.19, I think.
Yeah, so I think we really agree with all the things you're saying here. It's just that the thing I find confusing in what you're just showing is that the point where this crossover happens actually seems to depend quite sensitively on doping, and that
No, it doesn't. It doesn't.
it shifts, right?
No, it's
point
confused.
where it,
No. See, what so what's confused? This is exactly this point about the critical fan. This point, this is not the crossover here. This point here, where it's flattening, that's more like you're actually entering a pure T-linear regime. And what I'm showing here is there is no feature here. So by the time you get to 0.22, that's here. There is no feature. But if you look here, which is the different dopings, so this is 0.26, 0.29, and 0.33. The scale is actually, I mean, it's pretty similar. So I don't think it's not that there's some. It's not that there's some fan. It's more like that it's constant, and that it does this, and the fan is something. The fan is something different. I believe, but so, yeah. So right. Yeah, I should have put. And if you look at I do have the data for like 0.24 and stuff. Like there is a little kink, and it is at around this same scale, not up here. So this is a different. I believe this is a different feature. Probably. Right. So already here, it is quite this sort of featureless line is quite confusing, I think.
Okay. I'm gonna stop the recording, so I'm gonna thank you. And
thanks, organizers.
let's give a minute in case